Welcome, everyone. Today we take a deep dive into reinforcement learning, or RL, a family of methods that is fundamentally different from the supervised and self-supervised approaches we have studied so far. In supervised learning, we hand the model a labeled dataset and ask it to imitate the correct answers. In reinforcement learning, there is no fixed answer key. Instead, an agent interacts with an environment, takes actions, receives feedback in the form of rewards, and gradually learns a behavior that maximizes long-term reward. This is learning by trial and error, guided by consequences rather than by labels. By the end of this lecture, you should be able to describe the agent-environment loop, define states, actions, and rewards, write down the return and the queue function, explain how a policy chooses actions, distinguish value learning from policy learning, understand deep queue networks and policy gradients, and connect all of this to real applications in robotics, games, and global health. Let's begin with the intuition. Reinforcement learning is the topic that ties together autonomy, decision-making, and learning from interaction. Keep one idea in mind as we proceed. RL is about learning to make a sequence of good decisions over time, not just a single prediction. The central motivation for RL is learning in dynamic environments. The image here shows a robotic assistant standing in a busy clinical setting, with clinicians and a patient in the background. Many of the most valuable applications of AI in health and medicine are not to solve static classification tasks, but sequential decision-making problems in environments that change over time and respond to how individuals and environments react in this context. Think of adjusting a drug dose over successive visits, managing a supply chain as demand fluctuates, or controlling a surgical robot as tissue deforms. In each case, the best action now depends on the state of the world, and each action changes that state, which changes the best next action. That coupling between action and environment is exactly what reinforcement learning is built to handle. Reinforcement learning has produced some of the most striking demonstrations in modern AI, spanning robotic surgery, strategy games, and real-world control. On the left is robotic surgery, where a learned policy can help guide instrument motion. On the right is one of the landmark moments in the field, DeepMind's AlphaGo defeating the world's champion for Go, the player Lee Sedol in 2016. The board shown here, with AlphaGo and Lee Sedol on the clock during a Google DeepMind challenge match, marked the point where reinforcement learning, combined with deep neural networks, surpassed the best human players at a game long considered a grand challenge for AI. These are not toy results. They demonstrate that RL can master environments with enormous complexity and long horizon strategy. Now let's build the vocabulary of reinforcement learning, starting with its most fundamental element. The first key concept is the agent. The agent is the decision maker, the entity that observes, chooses actions, and learns. It might be a robot, a game-playing program, a treatment recommendation system, or a logistics controller. The core action of an agent is captured right here on the slide. Agents take actions. Everything else in RL is defined relative to this agent, and the choices it makes. Notice that agent is written with a lowercase s in parentheses, simply to indicate that we may have one agent or many. In multi-agent settings, several agents interact simultaneously. Next, we introduce the environment. The environment is the world in which the agent exists and operates. As stated here, it could be the real world or a simulacrum, meaning a simulation. This distinction matters enormously in practice, because RL learns by trial and errors can be costly or dangerous in the real world. We very often train agents first in high-fidelity simulators, then transfer the learned policy to reality. The agent and environment together form a closed loop, and that loop is driven by actions. Actions are the operations or steps that an agent takes in the environment, denoted as subscripta t, the action at time t. The action space, written capital A, is the set of all possible actions a specific agent can take. This set can be discrete, such as move left, move right, or stay, or it can be continuous, such as a steering angle or a drug dose in milligrams. The size and structure of the action space strongly influence which RL algorithm is appropriate, a point we will return to later. Now we complete the loop by adding what flows back from the environment to the agent. After the agent takes an action, the environment returns observations along the top of the loop. Two quantities matter here. The next state, written S subscript t plus 1, representing the state changes that result from the action and the reward, written R subscript t. Three careful definitions are laid out for us here. Observations are assessments of the environment after taking actions. States are the observable internal or external parameters or situations that the agent can perceive. And rewards are feedback that measures the success or failure of the agent's actions. So the loop is, the agent observes a state, takes an action, and the environment responds with a new state and a reward, and this repeats step after step. This state action reward next state cycle is the beating heart of every reinforcement learning problem, and it is formalized mathematically as a Markov decision process, defined by states, actions, transition probabilities, rewards, and a discount factor. Now we need to define what the agent is actually trying to maximize, and here, the discount factor enters. The agent does not simply maximize the immediate reward, it maximizes the discounted total reward, called the return, written capital R subscript t. The formula shows the return as a sum, from time I equals t to infinity, of gamma to the power I times R subscript I. Expanded, that is gamma to the t times R at t plus gamma to the t plus 1 times R at t plus 1, and so on into the future. Gamma is the discount factor, and it lies strictly between 0 and 1. The discount factor encodes how much we value future rewards relative to immediate ones. A gamma near 0 makes the agent myopic, caring only about the next reward. A gamma near 1 makes it far-sighted, weighing long-term consequences heavily. Discounting is not just a modeling preference. Mathematically, it keeps this infinite sum finite and well-behaved, and it reflects genuine uncertainty about the distant future. This notion of return is the quantity we want to optimize, but to act well, we need a function that tells us the value of choices, and that brings us to the Q function. Let's now define the Q function, one of the central objects in reinforcement learning. At the top, we again see the return R subscript t, the discounted sum of all rewards obtained over time, t. Below, it is the definition, Q of S subscript t and the subscript t equals the expected value of the return, given that we are in state S at time t and take action AE at time t. In words, the Q function, also called the action value function, aims to capture the expected total future reward that an agent in a given state can receive by executing a certain action. The state is shown in gold and the action in green, a color convention the slides use throughout. The key idea is that Q attaches a number to every state action pair. How good is it to take this action from this state, accounting for all the reward that will follow if we continue acting well? If we knew the true Q function, we would have a powerful basis for decision-making, which raises the natural question of how to turn Q values into behavior. So, how do we take actions given a Q function? The Q function tells us the expected future reward for each state action pair, but the agent still needs a rule for choosing. That rule is called a policy, written pi of S, which maps each state to an action. For this algorithm to work, as noted here, the agent needs a policy pi of S to infer the best action to take at every state. The strategy of a good policy should choose an action that maximizes future reward. This gives us the optimal policy, written P star of S, defined as the argmax over actions AA of Q of S and A. Argmax means look across all possible actions from this state and select the one with the highest Q value. In principle, if we have the correct Q function, this greedy policy is optimal. In practice, of course, we do not start with the correct Q function. We must learn it, and this is where deep reinforcement learning enters. There are two broad families of deep reinforcement learning algorithms, and they are contrasted side by side here. On the left is value learning. Here we find Q of S and A, and then act by taking a equals, the argmax over actions of Q of S and A. In value learning, we learn the value function first, and the policy is derived from it, choosing the highest value action. On the right is policy learning. Here we directly find the policy pi of S, and then sample an action AA from pi of S. In policy learning, we learn the policy directly, often as a probability distribution over actions, and we sample from it. This distinction is fundamental. Value-based methods, like Q-learning, are excellent when actions are discrete, and we can enumerate and compare their Q values. Policy-based methods shine when actions are continuous or when we want a genuinely stochastic, probabilistic policy. We will explore both, beginning with the value learning side. Let's dig deeper into what makes learning the Q function hard. On the left, a simple scenario is posed in a breakout-style game. From a given state, we consider option 1, where the paddle stays put beneath a falling ball, and option 2, where the paddle moves toward the ball. On the right, the same idea is posed as a question over the game screen. Which state action pair generated a higher Q value, moving the paddle left or moving it right? The takeaway is stated plainly. It is usually non-trivial to accurately estimate Q values over long event sequences. The difficulty is that a single action's true value depends on everything that happens afterward, sometimes many steps later, when the ball finally hits or misses the bricks. This is the credit assignment problem, and it is exactly what a deep Q network is designed to tackle, by learning to approximate Q with a neural network. Consider now the two ways a deep Q network, or DQN, can be structured, both illustrated on Atari. On the left is the first option. The network takes state plus action as input and outputs the expected reward. That is a single Q value, Q of S and A, for that specific pair. On the right is the second, more common option. The network takes only the state as input and outputs the expected reward for all possible actions at once, giving Q of S and A1, Q of S and A2, on up to Q of S and AN. This second design is sufficient because a single forward pass yields the Q values for every action, so we can immediately pick the best one. At the bottom is the learning objective, the Q loss. The loss is the expected squared difference between a target and a prediction. The target is R plus gamma times the maximum over next actions. A prime of Q of S prime and a prime. The prediction is Q of S and A. This is the Q-learning update in its deep form. We nudge our current estimate Q of S and A toward the observed reward R plus the discounted best value achievable from the next state. In tabular Q-learning, this is written as Q of S, gets updated to Q of S, a plus alpha times the quantity, R plus gamma times the max over A prime, of Q of S prime, A prime, minus Q of S, A, where alpha is the learning rate. In practice, stable DQN training relies on two crucial engineering tricks not fully shown here. Experience replay, which stores past transitions in a buffer and samples them randomly to break correlations between consecutive samples and a separate target network. A slowly updated copy used to compute the target so that the learning target does not chase a constantly moving prediction. Let's summarize the complete DQN loop. In short, a DQN is a network that learns the Q function and uses it to infer an optimal policy PA of S. The state, an Atari frame, feeds into the neural network, which outputs a Q value for each action. Here Q of S, A1 equals 7, Q of S, A2 equals 15, Q of S, A3 equals 10, Q of S, A4 equals 4, and so on down to Q of S, AN equals 1. The policy then selects the action with the highest Q value, pi of S equals the argmax over A of Q of S, A, which in this example is a 2, with a value of 15. The agent sends that chosen action back to the environment and receives the next state, closing the loop and continuing the cycle. One practical note, because the policy usually takes the argmax, a pure greedy agent never tries alternatives, so real training uses exploration, most commonly epsilon greedy, where with a small probability, epsilon the agent picks a random action instead of the best one. This balances exploitation, using what it knows, against exploration, discovering whether some other action is actually better. Despite its successes, Q-learning has important limitations. The slide lists them. DQNs are well suited for problems where the action space is small and discrete. They cannot typically handle continuous action spaces. Their policy is deterministically calculated from the maximization of the reward, that is, from the Q function, and stochastic or probabilistic. Policies are not typically learnable by DQNs. These are real constraints. If your action is a continuous steering angle, you cannot take an argmax over infinitely many actions. And if the optimal behavior is inherently random, a deterministic argmax cannot represent it. We can do better then, so let us consider another class of RL training algorithm, the policy gradient method. Here is the key idea behind policy gradient, or PG methods. Rather than learning Q values and then taking an argmax, the policy gradient method directly optimizes the policy pi of S. The diagram looks similar. A state feeds a neural network, but now the interpretation changes. Instead of treating the outputs as fixed Q values and greedily selecting the maximum, the network defines a probability distribution over actions. The policy is written pi of S is distributed according to P of a given ES, and here the network's outputs are interpreted as probabilities. The probability of each action given the state, with the constraint that the sum over all actions AI in A of P of AI given S equals 1. So instead of always choosing the single highest value action, the agent samples an action according to these probabilities, for example landing on a 2. The grayed out argmax formula at the bottom right reminds us of the value learning approach we are now replacing. This shift from deterministic selection to a learned probability distribution is exactly what lets policy gradients represent stochastic policies. And crucially, policy gradients also unlock continuous action spaces. Let's see how the policy gradient method enables the modeling of a continuous action space. Instead of outputting a probability for each discrete action, the neural network outputs the parameters of a continuous probability distribution, here a Gaussian, a mean, mu, equals -1, and a variance, sigma squared equals 0.5. The policy P of a given S is then the normal distribution N of mu and sigma squared, shown as the familiar bell curve over a continuous action axis running from faster left to faster right. To actually act, the agent samples from this distribution. Because it is continuous, we integrate rather than sum. And the integral from minus infinity to infinity of p of ai given s equals 1. A sampled action might be minus 1.2 meters per second, a specific continuous velocity. This is powerful. With a single mean and variance output, the agent can command any real-valued action and can even control its own exploration by widening or narrowing the variance. This directly addresses the DQN limitation we saw earlier. Let's make the discrete versus continuous contrast explicit. On the left is a breakout state. On the top right, a discrete action space, shown as a set of categorical direction options. Large left, stay, small right, large right, each with a probability represented by a bar, over a left to right axis. On the bottom right is a continuous action space, shown as a smooth Gaussian, over direction, and continuous magnitude, from faster left to faster right. A labeling caveat. Both the top and bottom right are labeled discrete action space, but the bottom panel, showing a continuous distribution over magnitude, should read continuous action space. That is a typo. The essential message is that discrete action spaces are handled naturally by categorical distributions and value methods, whereas continuous action spaces require the continuous distributions that policy gradient methods provide. Let's ground policy gradients in a concrete health-relevant case study. Here, a surgical robotics example is placed into the standard agent environment loop we built earlier. The agent takes actions, the environment returns observations, the next state S subscript t plus 1, and the reward R subscript t. The environment here, from Barrier and colleagues, 2020, is a surgical suturing task, showing multiple patient side manipulators, or PSMs, a suture needle, and a thread, with the desired trajectory in green, the generated trajectory in red, and the suture thread annotated. This is exactly the kind of continuous control, high-stakes sequential decision problem where policy gradients are appropriate. The action is a continuous motion of the instrument, and the reward encodes how closely the generated trajectory follows the desired one. It also illustrates why we often train in simulation first before approaching a real patient. Now let's look at the policy gradient training algorithm step by step. The procedure has 6 steps. 1. Initialize the agent. 2. Run a policy until termination, meaning let the agent act through a complete episode. 3. Record all states, actions, and rewards along that trajectory. 4. Decrease the probability of actions that resulted in low rewards. 5. Increase the probability of actions that result in high rewards. And 6. Adjust the agent, that is, apply a gradient descent update to its parameters. On the right, the surgical trajectory is annotated with the sequence of state action reward tuples S0, A0, R0, S1, A1, R1, and so on, comparing the RL learned trajectory in solid red against the user trajectory in dashed green. The intuition is beautifully simple. Whatever the agent did on good episodes, make it more likely. Whatever it did on bad episodes, make it less likely. This is the essence of the reinforce algorithm, and the next slide gives it precise mathematical form. Here's the policy gradient loss that makes steps 4 and 5 precise. Steps 4 and 5 are highlighted in gold to show they correspond to this equation. The loss equals minus the log of p of a subscript t given s subscript t times r subscript t. 2 factors are labeled here. The first is the log likelihood of the action under the policy, and the second is the reward, the return. The update rule follows at the bottom. W prime equals w minus the gradient of the loss, which expands to w prime equals w plus the gradient of log p of a t given st times r subscript t, labeled the policy gradient. Read this carefully. Because we multiply the log probability gradient by the return, actions followed by high return get their probability pushed up, and actions followed by low return get pushed down. When the return r is large and positive, we ascend the log likelihood of that action, making it more probable. When r is small or negative, we do the opposite. This single elegant rule is the foundation of policy gradient methods, and in more advanced forms it becomes the actor-critic family, where an actor learns the policy and a critic learns a value function, to reduce the variance of these updates and stabilize learning. Now let's move from the mathematics to applications, and see reinforcement learning in the real world. Having built up states, actions, rewards, returns, Q functions, policies, DQNs, and policy gradients, we now look at what these methods actually achieve in practice. Our first real-life example is a provocative cautionary one about why exploration is dangerous outside simulation. The 6-step policy gradient loop appears again, but notice step 2. It states we should run a policy until termination, highlighted in red. Say the task is to drive a car autonomously, or even worse, a self-driving ambulance. What could happen if this vehicle were speeding along a mountain road without the right policy could be disastrous. The point is that ruining a policy until termination sounds harmless in a simulator, but this in the real world can be significantly riskier. This is precisely why we prefer to explore and fail inside simulations, where a catastrophic action costs nothing, before deploying to physical systems where failures are expensive, unsafe, or irreversible. The lesson is unmistakable. In real-world reinforcement learning, safe exploration is not optional. The trial and error that works so well in simulation can be catastrophic when the environment is a real vehicle, a real patient, or a real piece of critical infrastructure. This motivates the whole field of safe RL, sim-to-real transfer, and careful reward design. Reinforcement learning also enables real surgical robotics, as shown here. The left panels depict a surgical robot platform and its instrument components, an operator console, with a phantom patient, and a handheld tool. On the right is an intraoperative photo, captioned as reinforcement learning in action, where, as the caption from Richter and colleagues, 2020, notes a learned policy was used. This is a direct link back to our policy gradient case study. The trajectories learned in simulation can drive real instrument control. It underscores both the promise, superhuman precision and consistency, and the responsibility, rigorous validation, of deploying RL in a clinical setting. Take a look at this animated example, one of the most famous demonstrations of RL for dexterous robotic manipulation from OpenAI. The animation shows a robotic hand, OpenAI's Dactyl system, manipulating a cube in midair. Across the animation, the hand reorients the cube to match a series of target orientations. First, it rotates the block so the face reading EI is shown to reach goal 1. Then it continues turning the cube to display the face in the same orientation as the displayed cube, in the bottom right to reach goal 2, and so on, through successive goals. The smaller inset shows the same policy reorienting a different object. What makes this remarkable is that the control policy was trained almost entirely in simulation, using domain randomization to vary physics and appearance, and then transferred to the physical hand. This means the physics of every single finger and wrist actuator, the feedback loop between the propriosensing pressors, sensors in their robotic fingertips, as well as the visual, to mechanical feedback, the camera steams to control the behavior of the system. All was learned with minimal or no prior, relying completely on simulation and real-world trial and error. It is a vivid illustration of continuous high-dimensional control, learned by reinforcement learning, exactly the regime where policy gradient and actor-critic methods dominate. Reinforcement learning has also produced agents that outperform humans across an entire suite of games, as shown by Agent 57. The animation is a large montage of dozens of different Atari and arcade-style games playing simultaneously. Platformers, shooters, racing games, puzzle games, all in motion at once. Agent 57, which emerged from DeepMind's large-scale competitive agent deployment and testing, was the first AI agent ever to exceed the human benchmark on most of the 57 canonical games in the Atari suite, including notoriously hard exploration games. The chart on the right ranks the games by the agent's score relative to human performance, with a line marking the human baseline. The significance is that a single learning algorithm, without game-specific engineering, learned to master an enormously diverse set of environments, from reactive arcade games to those requiring long-term planning and exploration, which is a strong signal of generality. Now we turn to the game that, for many, defined the arrival of modern reinforcement learning: Go. The goal of Go is to obtain as much board territory as possible to beat the opponent. The table makes the central challenge vivid by counting board positions as a function of board size, n by n, where the number of naive positions is 3 to the power n squared. For a 1 by 1 board, there are 3 positions, of which 33.33%, that is 1, are legal. For 19 by 19, standard Go, there are on the order of 1.74 times 10 to the 172 possible position encodings, of which about 1.2%, roughly 2.08 times 10 to the 170, are legal. The punchline is at the bottom. There are a greater number of legal board positions than atoms in the universe. This astronomical state space is why brute force search fails, and why Go resisted AI for so long. You simply cannot enumerate the possibilities, so the agent must learn intuition and evaluation, which is exactly what deep reinforcement learning provides. Let's see how AlphaGo actually beat the top human player at Go in 2016, combining supervised learning with reinforcement learning. The pipeline has 3 stages. First, initial training on human data. Starting from human expert positions, a supervised learning policy network is trained by classification to imitate expert moves. Second, self-play and reinforcement learning. The policy network is improved through repeated self-play, where the system plays against versions of itself, producing an RL policy network that reaches superhuman performance. Third, from self-play data, a value network is trained by regression to evaluate board states, giving the system an intuition about the board state, that is, an estimate of how likely each position is to lead to a win. The Netflix documentary AlphaGo, referenced by the still on the lower left, tells this story. The deep lesson is architectural. AlphaGo bootstrapped from human knowledge, then transcended it through self-play reinforcement learning, and used a learned value function to evaluate positions that could never be exhaustively searched. The same DeepMind lineage produced a breakthrough far beyond games, AlphaFold 2. As the headline structure solver text explains, DeepMind's AlphaFold, two algorithms significantly outperformed other teams at the CASP14 protein folding contest, and improved dramatically over its own previous version at the prior CASP. The chart plots the global distance test score, GDT_TS, across contest years. A score above 90 is considered roughly equivalent to the experimentally determined structure. AlphaFold 2, the tall orange bar in 2020, reaches into the high 80s, a step change above all prior methods. The right panel reviews the protein structure hierarchy the model must predict. Primary structure, the polypeptide chain. Secondary structure, alpha helices and beta sheets formed by hydrogen bonds. Tertiary structure, the overall three-dimensional fold. And quaternary structure, multi-subunit complexes. The significance for global health is enormous. Accurate protein structure prediction accelerates drug discovery, enzyme design, and our understanding of disease at the molecular level, and it grew directly out of the deep learning and reinforcement learning research culture we have been discussing. Let's situate today's lecture within the full course. Reinforcement learning is a natural fit for logistics, supply chain, and resource allocation problems, deciding how to distribute limited vaccines, staff, or diagnostics across a dynamic system over time. You can see how this lecture builds on everything before it, from baseline machine learning through neural networks, computer vision, sequence and language models, GANs, and graph neural networks, and connects forward to fairness, applied global health cases, and regulation. Reinforcement learning is one powerful tool in this broader ecosystem, and the strongest global health solutions usually combine several of these methods. Here are the resources for going deeper. For bibliography, the recommended reading is Chapter 13 of Deep Reinforcement Learning Hands-On by Maxime Lapin, an excellent practical, code-first treatment of DQNs, policy gradients, and actor-critic methods. For software, the slide points to Google Colab at colab.research.google.com, which lets you experiment with RL environments and train small agents without configuring a local GPU. Nothing builds intuition for exploration faster than watching your own agent learn, or fail to learn, and then debugging why. That brings us to the end. To wrap up, reinforcement learning teaches an agent to make good sequential decisions by interacting with an environment and maximizing discounted future reward. The core loop is state, action, reward, and next state, formalized as a Markov decision process with a discount factor gamma. The Q function captures the expected future reward of a state-action pair, and the policy turns those values into actions. Value learning, with deep Q networks, experience replay, and target networks, works well for small discrete action spaces, while policy gradients directly optimize the policy and handle stochastic and continuous actions, extending to actor-critic methods. We saw these ideas power robotic manipulation, surgical robotics, Agent 57 across all 57 Atari games, AlphaGo's historic victory, and AlphaFold's protein folding breakthrough. And we discussed why safe exploration and simulation matter so much before real-world deployment. As you take on your projects, ask 3 questions of any RL system. What are the state, action, and reward? Is the action space discrete or continuous? And how will the agent explore safely in a high-stakes health setting? That brings us to the end. Thank you again for your attention, and see you next time.